Alrighty, welcome to Algebra 1 video on simplifying square roots and combining different terms with square roots. So this video is something you'll probably cover just after having learned solving equations with x squared. And the reason it follows that is because you've just learned about branching and taking the square root of both sides. So now you're going to learn different ways to deal with the square root of numbers that aren't perfect squares. So for example, if when you take the square root of both sides you have like a 64, you take the square root of that and you get plus or minus 8. But it's possible that in some situations, the number that you're taking the square root of will not be a perfect square. Like, what if it was square root of 90? Like, what do? Oh crap, it's not a perfect square. So this video will teach you how to deal with taking the square root of things that are not perfect squares. So it's called simplifying square roots, and it's valuable anytime it's not a perfect square that you have memorized. So if you're solving an equation with something squared, and whatever is inside of there, you're going to set equal to plus or minus of some number. If that number is not a perfect square, this is what you want to do. So you kind of have two choices. The first one is like the cop-out. I'll call this cop-out. That means you're being lazy. You could get a calculator out and you could just type it in, square root of 37 or square root of 90 or whatever it is, and you can get a decimal value that you have to round. But typically we want to avoid rounding because that's less accurate than getting exact values. So typically our preferred method is to reduce the square root to simplest form, and there's just one rule that you need to know that will enable you to do that. So the rule is this: the square root of a product of two numbers is equal to the square root of the first number times the square root of the second number. So you might be wondering, how is that going to help me? And I'll show you right away that that's very, very helpful. The reason is, even though the number a times b, whatever the original number is, may not be a perfect square, if you can factor it so that it's a product, or two perfect squares multiplied together, or at least one of these two is a perfect square, then you can take the square root of that part. So I think the easiest ways for you to see what I'm talking about is to start with an example and then do even more examples. Okay, so suppose you have square root of 90. Okay, obviously 90 is not a perfect square, but you could write 90 as a product. So you're basically factoring this into 9 times 10. So we all know that 90 is 9 times 10. So this is the same as the square root of 9 times 10. The square root operation occurs last. So you don't have to put parentheses here, but it's as if there was parentheses right here. So the square root of 90 is the same as the square root of 9 times 10. Okay, and according to this rule right here, we could write that as the square root of 9 times the square root of 10. Okay, and breaking that apart into those two pieces is what's really valuable, because now the square root of 9 is just 3. You know that. And the square root of 10, can we simplify that? No, we can't. So it's 3 root 10. And so that would actually be your final answer. You might be wondering, well, why don't I keep going? Why don't I break the square root of 10 down? Well, the square root of 10 is the same as 2 times 5. But neither 2 nor 5 is a perfect square. So even if I broke it down, like let me write it down, I could write 3 times the square root of 2 times the square root of 5. I could break it down using this rule. But neither the square root of 2 nor the square root of 5 is something that I can simplify. So having it as 3 root 10 is better than having it as 3 root 2 root 5, even though technically these are both the same answer. So if you can simplify it, you want to simplify it. If the number that's left over under the radical can't be broken down into any perfect squares, then you're done. Okay, so that was example 1. Let's do another one, example 2. The square root of 32. Okay, so think about 32. What's 32? You want to factor it into something that's a perfect square. So, I mean, you could write 8 times 4, and that's true because 4 is a perfect square. But to do it all at once, you want to factor it into the biggest square possible. So actually, 16 times 2 is a great choice. So this is the square root of 16. Actually, let me make my square root symbol bigger. 16 times 2, which is the square root of 16 times the square root of 2, right? So we took one square root and we broke it into two square roots. Let me kind of separate this problem off here. And now this part we can solve. The square root of 16 is 4. The square root of 2 can't be simplified, so we leave that as a 2. And we write the answer as 4 root 2. So all of these problems, you're not actually solving it and getting like a decimal value or a whole number. You're still going to have square roots in your answer, but the square roots in your answer are going to be simplified as much as possible. So what I wrote here is reduce the square root to simplest form using this rule. So it's still going to be a square root, but 4 times the square root of 2 is simpler or reduced from the square root of 32. So the number under the square root is going to get smaller and smaller and smaller until it can't be reduced any further. So let me erase these two actually, and then I'll try to do a couple of more examples. Okay, so we're back and we're going to do a couple more examples. Try the square root of, I don't know, 1,000. Okay, we can write that as the square root of 100, which is a perfect square, times 10, which is not a perfect square. And now we can break it apart as the square root of 100 times the square root of 10. This one is a perfect square, that's just 10. Square root of 10 we can't simplify, so it's 10 root 10. And you pronounce this 10 root 10, or 10 radical 10. You could say 10 times the square root of 10, but that's a whole mouthful, so it's a lot easier to say 10 root 10. Okay, how about another example, number 4? What about, let me think of a good one here, 72, square root of 72. Okay, you could write this as the square root, 72 is the same as 36 times 2, if you break it apart. So you're going to have to be good at factoring here. 36 times 2. Now, on this one, let's just go straight to the answer. Okay, you could write this step here where you break it apart and you write the square root of 36 times the square root of 2, but in your head you should be getting comfortable saying that this square root symbol applies to the 36 and it also applies to the 2. So the square root of 36, that's just 6. The square root of 2, we can't simplify that. You know, if you're not comfortable going straight from here to here, that's okay. Go ahead and write out an extra step similar to this one here, where you write out the square root of 36 times square root of 2. But if you're comfortable, you can go straight to this kind of answer. Okay, let's do one last one. Let's do the square root of 8. Square root of 8 is the same as the square root of what? 8 is the same as what times what? 4 times 2. Okay? The square root of the 4, that's just 2. The square root of 2, we can't simplify, so it goes like that. The final answer. And I guess I have one more that I want to do, which is something like this. Do square root of 21. Okay. 21 factors into 3 times 7. Okay. And you say, uh-oh, square root of 3, that's not a perfect square. Square root of 7, that's also not a perfect square. So neither one of these is a perfect square, and neither one can be broken down any farther. So if this happens to you, what that means is, go back to your original problem. The square root of 21 cannot be reduced. So you can only reduce the square root if it's made up, or if when you factor it, you get perfect squares. If the number here is a product of things that are not perfect squares, then you can't simplify it, and you're stuck just leaving it as a square root of 21. So square root of 21 is already in simplest form. Alright, so this is how you simplify square roots. Now, in the next small segment, we're going to see how to combine different terms that have square roots in them together. Alright, so combining terms with square roots. Fortunately for you, combining terms with square roots is exactly the same as combining like terms with variables. If you think of square root of a number as some unknown. So let's take a look at the formula first for adding and subtracting. When you were adding and subtracting variables, you know that there had to be like terms, which meant the base and the exponent matches up. The same is true when you're adding or subtracting square roots. The square root part has to match up with the square root part. So here, I've got the square root of x, and here I've got the square root of x. So these are like terms. They match up. The part under the square root is the same. So if I'm adding some number of square root of x's to some other number of square root of x's, I just add my numbers a and b. Let me put a concrete example here. 3 root 2 plus 6 root 2 equals. So root 2 is kind of like my object. Pretend that root 2 is a frisbee. Okay, 3 frisbees plus 6 frisbees equals 9 frisbees. But instead of a frisbee, I have this thing root 2. So 3 root 2 plus 6 root 2 equals 9 root 2. Whatever was the square root part stays the same. When you're adding and subtracting, all that will ever change is the coefficient. Doesn't matter whether you're adding and subtracting things with square roots, adding and subtracting variables with exponents. In both cases, the coefficient, which is the number in front, that's the part that you'll add or subtract, but the variable or the part under the square root, you'll not change at all. It's just the object that you have, and the coefficient is how many of them you have, which is what's changing when you add or subtract. So that's one example. Let's try another example. 12 root 6 minus 14 root 6. Okay. The part here matches up, so we're able to combine them. And we do the coefficient. 12 of them minus 14 of them is going to be negative 2 of them. And what are they? They are root 6's. Okay. Let's try one more example. Suppose I have 2 root 8 plus plus 7 root 2. Okay. At first, you'll look at this and you'll say, ah, Morgan, root 8 and root 2, those are different, so I can't combine them. But then you have to think to yourself, what did I just learn right before this? I learned that root 8 is the same as 2 root 2. So the part that's under my square root, if I could simplify it from what we just learned before this, I should simplify it because that might allow me to combine two things that looked like they wouldn't be able to be combined. So in place of the root 8, I could write 2 root 2. Okay, so this root 8 right here, let me make some space. Oh, that's not going to work. I'll just write it here. This is 2 times 2 root 2 plus 7 root 2. Okay, this again, this part right here, came from this right here. So this right here equals this right here. Okay, what's 2 times 2 root 2? We haven't gotten to this yet because it's in the next part, but I'll just tell you right now. 2 times 2 root 2 is 2 times 2 is 4, so it's 4 root 2. So this right here is 4 root 2, and I'm adding to it 7 root 2, so 4 root 2 plus 7 root 2 is, wait for it, 11 root 2. So I apologize that I got slightly ahead of myself there, but at least I hope this first part made sense. You try to add these two, you notice that they don't match up, so you see if you could reduce this one so that they do match up. Sometimes they won't match up, and you can't reduce them, and then there's no way to combine it. So sometimes the answer is that you can't combine them, or it's already in simplest terms. But if it looks like you can't combine them, you should definitely check and see if one of them could be reduced so that they match up, and then you can add them together like we did here. So again, adding and subtracting combine like terms, which means the part under the radical, the number under the radical, should match up. Okay, so the other possibility here, the other possibility is multiplying and dividing. So the stuff on the outside stays on the outside, and the stuff on the inside stays on the inside. Let me clear a little bit of space, and then we'll go through this in a little bit more detail. All right, good. suppose that you've got a product of two things that have square roots. So a root x times b root y. This could be something like 2 root 3 times 6 root 4. Except the root 4 is just 2. So let's do 6 root 5. Okay. Keep stuff on the outside stays on the outside. Okay, when I say outside, I mean not under the square root symbol. So this 2 is on the outside, and this 6 is on the outside, and I'm multiplying them together. So what's 2 times 6? 2 times 6 is 12. Okay. Stuff on the inside stays on the inside. What's on the inside of this radical? A 3. What's on the inside of this radical? A 5. So underneath the radical, I have 3 times 5, which is the same as 15. So 2 root 3 times 6 root 5 is the same as 12 root 15. That's a lot like, I'll just write one here quick, 2x times 6y. 2 times 6 is 12. X times y, you just write x times y. If they're x's and y's, you can't combine them, so you have to write x times y. But if they're numbers, like root 3 and root 5, we could combine them underneath the square root symbol, because remember we just learned in the previous section that root 3 times root 5 is the same as root of 3 times 5. So because they're numbers, we can combine them together under the square root symbol, whereas if they were variables, we would just write x times y and we couldn't combine them at all. Alright, excellent. Sorry, I'm trying to clear some more space out, so I'll get rid of this. Okay, how about when you divide? So dividing is pretty much the same as multiplying in terms of keeping stuff on the outside outside, keeping stuff on the inside inside. So whatever your two numbers were that were in front of the square root symbols, you divide those two numbers, but you keep them on the outside of the square root. And whatever numbers you had underneath the square root symbols, you divide them, but you keep them under the square root symbol. So an example of this one is going to be, let's do 12 root 18 over 4 root 2. Okay? So these numbers are outside the square root symbol. 12 divided by 4, that's just 3. Now, the square root symbol has an 18 and a 2. So this rule says square root of one number divided by a square root of another number is the square root of whatever the quotient is. So the square root, what's 18 divided by 2? Well, that's just 9. And now this is even cooler because what's the square root of 9? This is 3 times square root of 9 itself. That whole thing is just 3 again. What's 3 times 3? 9. So sometimes you get lucky, and even though your starting off problem has radicals in it that do not reduce, they might combine in just such a special way that your final answer comes out to be a whole number. So when that happens, it's kind of cool, and you should be happy. Alright, I think that covers all the basics. You can add, subtract, multiply, and divide any terms that have square roots in them. You're following the same rules you learned with exponents, except now if they're numerical values, you can combine them into the square root symbol. You've also learned how to simplify square roots. So you can simplify square roots by factoring the inside into a product of two numbers, and the idea is that one of those numbers is a perfect square. So take some number, factor this one number into a product of two numbers, so that either this one or this one of these two numbers is a perfect square. And if it's a perfect square, you can take the square root of it, and now the square root symbol is gone for that portion, but the square root symbol is still there, the radical is still there for the other part that was not a perfect square. Okay, I'm going to run through a couple of more examples in this last bit of space that I have remaining to me, and these examples will cover a little bit of everything. Alright, let's test your understanding. Example 1. So let's do 3 root 5 minus 8 root 5. Okay? These are like terms. We're adding or subtracting, so we just have to make sure that the number under the square root's the same, and then we combine the coefficient. So I have 3 of these things, 3 of these root 5 objects. Root 5 could be a dandelion or a flower of some other sort. So 3 flowers minus 8, say flowers, equals, well, what's 3 minus 8? 3 minus 8 is negative 5. And negative 5 what? Negative 5 of these flower objects, which look like square root of 5 suspiciously. Okay, so adding and subtracting combine like terms. How about, what if it just says simplify the square root of 242? Holy smokes. Simplify the square root of 242. Okay, well, 242 could be broken down into 121 times 2. Okay, so square root of 242 is the same as the square root of 121 times 2. And this right here, my friends, this is a perfect square. The square root of 121 is just 11, but the square root of 2 is trapped. It's not a perfect square, so we can't take it out. So the square root of 242 could be simplified or rewritten as 11 root 2. Okay, let's do one more example. The product. 13 root 5 times 3 root 8. Alright, well, the stuff on the outside stays outside. What's 13 times 3? 13 times 3 is 39. And the stuff on the inside stays inside. Okay, what's 5 times 8? 5 times 8 is 40. Fantastic. So the product of these two pieces, 13 root 5 multiplied by 3 root 8, is going to give you 39 root 40. Now you might think you're done at this point, but anytime you have a product of square roots and the number underneath the radical is changing, you should always look at your answer and see if it's possible that it might be able to be simplified. So the square root of 40 could be written as 4 times 10, right? The square root of 4 times 10. And the square root of 4 is a perfect number. So what I have, let me write the 39 again. So I have 39 times the square root of 4 times 10. The square root of 4, well, that's just 2, right? So I have 39 times the square root of 4, which is 2. 39 times 2. And then I also have the square root of 10. Well, the square root of 10 is trapped inside because it's not a perfect square. So only perfect squares can be taken the square root and come outside. But anything that's a square root, a number under the square root that's not a perfect square, is I like to think of it as trapped inside. It can't come out. But the 39 is outside, and the root 4 became a 2. So what's 2 times 39? Well, 2 times 40 is 80, and 39 is just 1 less than that. So if we double that, it's 2 less than that. So 39 times 2 is 78. Okay, and so that will be our final answer for this problem and also for the video. So you've learned to add, subtract, multiply, and divide terms with square roots in them, and you've learned how to simplify square roots. So either at the beginning of the problem you might have to simplify a square root, or in the process of adding and subtracting and multiplying and dividing, you might want to simplify some as well. So I hope this has been helpful, and make sure you fill out the form, don't forget.